In this chapter, we begin our discussion of more traditional colloid science topics. The definition commonly used for a colloid is that of systems containing particles having at least one dimension within the size range of a nanometer to a micron. This simply reflects the observation that such systems typically demonstrate colloidal behavior, which could be described as a strong prevalence of processes that act to reduce surface area. We will elaborate on this shortly. There are systems of particles that fit this basic definition that do not demonstrate such proclivities. These systems, which were described in previous sections absent the label of colloid, are thermodynamically stable and will not be the focus here. Our discussion will examine systems formed through the combining of immiscible components, requiring that one phase be broken down and dispersed throughout the other. Such systems are not thermodynamically stable, but can be rendered kinetically stable through the use of additives such as surfactants, water-soluble polymers, and even small particles. These systems are known as lyophobic, or in water, hydrophobic colloidal systems. There are many systems you're familiar with that you may not have realized are colloids. A good example of this is milk. Milk is a colloid composed of milk fat globules dispersed by lipids in an aqueous solution. The triglyceride particles carry fat-soluble vitamins, for example vitamins A and D, and essential fatty acids. The fat particles in homogenized products have an average particle diameter of about 400 nanometers. Also contained in milk are carbohydrates, minerals, and proteins. Most of the protein is in the form of micelle structures known as casein. Another example of a colloid is a paper-making slurry. Although paper-making fibers have dimensions significantly larger than 1 micron, other components in production slurries, namely microfibrils and fillers, are within the colloidal size range. Furthermore, the fibers demonstrate aggregation behavior indicative of hydrophobic colloidal systems, behavior which is often controlled through the use of special additive polymers. Another example of a colloid, which is likely less familiar to you, is that of a nanoclay polymer composite. Clay particles are composed of stacked thin layers or plates. Clay is used in a variety of products, including cosmetics, adhesives, coatings, paper, foods, etc. Although often just outside the official size range, slurries of clay particles behave like a hydrophobic colloid. The individual plates composing clay particles are within the colloidal size range. Through combined chemical and mechanical treatments, the platelets can be dispersed in matrices such as polymers to act as reinforcements. Their high strength and high specific surface area can provide for enhanced mechanical properties of composite materials. The most common scheme for classifying colloids includes 3 categories. We have already discussed 2 of the 3 categories. This includes water-soluble polymers that are described as hydrophilic colloids. The random coils formed by the polymers in solution roughly produces outlines of particles with diameters in the nanometer size range. Because the polymers are dissolved in solution, such systems are thermodynamically stable. That is, for a fixed set of state variables, the system does not change. The other type of colloid discussed in the course are the micron-size micelle structures, which form at a particular surfactant concentration known as the surfactant's critical micelle concentration, or CMC. Micelles are a type of thermodynamically stable, self-assembled structures known as association colloids. Other examples of association colloids include vesicles and bilayers. This brings us to the final category of colloids, lyophobic colloids. Such systems consist of immiscible components in which one component is in the form of small particles and dispersed throughout the other. Given our emphasis on water, the focus here will be on systems involving water, so-called hydrophobic colloids. As will be discussed, hydrophobic colloids are not thermodynamically stable. They're only kinetically stable. In other words, these systems are metastable. Lyophobic colloids, consisting of all combinations of the various states of matter, solids, liquids, and gases, are possible with the exception of 2 gases. The nomenclature used to describe these various systems, along with a few examples, are shown here. Our discussion will focus on what is classically referred to as hydrophobic colloids, for which a water-immiscible solid, liquid, or gas is broken down in the form of fine particles and dispersed throughout an aqueous continuous phase. Such systems are known as sols, emulsions, and foams, respectively, which are found extensively in industrial applications. It should be emphasized that hydrophobic colloids are heterogeneous systems in that they are a mixture of immiscible phases, and they are inherently unstable. As we introduce hydrophobic colloids throughout this chapter, the focus will be on colloidal sols. Again, sols consist of small particles that are evenly dispersed throughout a liquid. Thus, hydrophobic sols consist of water-insoluble particles dispersed in water. Sols are generated either through mechanical reduction or a variety of synthesis or building up processes. The mechanical attrition of a solid into small particles is referred to as comminution. This is usually accomplished using equipment known as crushers and media mills. These apply mostly shear, impact, and compressive forces to solids under either wet or dry conditions. Although the surface or interfacial energy of a solid and the change in surface area can be used to estimate the reversible work required for the comminution process, this theoretical energy value typically accounts for less than about 1% of the energy actually consumed. A majority of the comminution energy is due to frictional losses in the equipment and the process stream, as well as energy dissipation within the solids that are being broken down. These produce heat and noise, some of which is lost to the surroundings, other retained within the process stream. A typical approach for producing a solid via building up involves precipitation. A homogeneous solution is supersaturated through changes in temperature, ion content, solvent composition, or other means, leading to nucleation and particle growth, or in general precipitation. This technique can be controlled through the use of additives that inhibit growth mechanisms and aggregation. This first example asks you to estimate the work required to break a waxy material of a given density down into micron-sized spheres in water. The interfacial energy between the material and water is provided. For such questions, often the number of particles formed from a mass is required, which can be found through a mass balance. With this and particle diameter, the change in surface area, neglecting that of the bulk material, is calculated, which is used to determine the reversible work. It was just stated that the reversible or theoretical work is a small percentage of the actual work involved, which includes irreversible processes. The surfactant reduces the interfacial energy and thus the reversible work, but it serves a more important role in its inhibition of the aggregation of the particles, which can significantly reduce the overall energy involved in the comminution process. The first obvious question associated with processes used to generate small particles is, what size are the resulting particles? It turns out that only in a few rare cases does this question have a simple answer. The reason is that most particles making up sols possess a wide variety of shapes and sizes. The shapes most often used to describe or model such particles are spheres, rods, and plates. The sphere is the simplest description, requiring only a single variable, the spherical diameter, indicated here with an uppercase D. Shortly, we will see how any given particle can be represented with the diameter of a sphere demonstrating similar properties as the particle, the so-called equivalent spherical diameter, or ESD. However, to begin, we will assume that all particles that we're looking at have a spherical shape. This eliminates one of the factors that complicates particle sizing. A second simplifying assumption is that we are applying a technique that provides us with accurate information on how such particles are distributed between various size categories, or size bins. This leaves us with the issue of polydispersity to contend with, which is where we begin this discussion. Results from the separation of particles based on size can be represented with its particle size distribution, or PSD. This is applied to the fraction or percentage of particles as a function of particle size. With relatively coarse measurements, this produces a histogram, with each bar representing the fractional number of particles ranging in diameter from a minimum value up to, but not including, a maximum diameter value. The fraction of particles within a given size range is calculated as the number of particles in this range divided by the total number of particles sorted. This is what is called a number-weighted distribution. The average particle diameter, or d bar, is calculated as the summation over all the bins of the number of particles within each bin multiplied by the average diameter of particles contained in that bin. This is then divided by the total number of particles counted. Using this average, the standard deviation then can be calculated. Note that the average particle size within each bin is often approximated as the midpoint of the bin. We could have also provided a maximum or minimum for the average using the maximum and minimum diameters of each bin. From the histogram, we can also identify the mode, which is the peak value in the histogram. In other words, the mode is the diameter range containing the most particles. As we increase the resolution of this measurement by decreasing the diameter range for a bin, the histogram starts to take on the appearance of a more continuous distribution of particle diameters, which eventually can be represented with a continuous function known as the frequency function. Identification of a continuous function changes the summation into integral equations for calculating average values and the standard deviations. We can also calculate what's called a cumulative distribution, which is shown here. From the cumulative fraction, it's easy to identify the median, which is the diameter that splits the distribution in half. That is, half the particles have diameters below this value and half above. The cumulative fraction can be determined from either a discrete or continuous distribution. The example outlined here is more typical of what you're going to be asked to do. A table of data are provided, and you're asked to construct a histogram and identify the average, standard deviation, mode, and median. Of course, there are different approaches for doing this. I've chosen to first calculate the fraction of particles represented by the individual counts. Using a total number of counted particles of 1,786, I found the following fractions and cumulative fractions. These are plotted on the right. From the plots, both the mode and the median can be identified. The equations provided earlier are then used to estimate the average and standard deviation. This is a bit of an estimate because the midpoint of the bin is used as the average for the particle diameters contained within the bins. As mentioned previously, it is also acceptable to use either the minimum or the maximum diameters for that bin and report the average as the minimum or maximum average, respectively. In addition to the mean, median, standard deviation, and mode, another measure used to describe particle size distributions is the diameter percentile, or d-value. Unless otherwise stated, the standard d-value is the undervalue. It indicates the diameter for which the indicated percentage of the distribution possesses smaller diameters. D10, D50, which is the median, and D90 are the three most commonly reported d-values. Span is another standard parameter reported for a PSD, gauged as D90 minus D10 over D50. This value provides information on the shape, precisely the width of the PSD. Weighted particle mean diameters provide views of a particle size distribution from a variety of perspectives. The dxy indicates the weighting factor applied. The three often reported are the number, surface area, and volume weighted means, designated D10, D32, and D43, respectively. So far, the discussion has focused on the fractional number of particles within a size range, number-weighted distributions. In general, we have indicated the fractional count with a small f. When we are specifically referring to a number count, we will use a small x to designate the fraction contained within a given bin. Using the designation scheme just reviewed, the mean for this type of distribution is D10, sometimes referred to as an unweighted mean. Also shown is the equation for the standard deviation for this distribution. Number-weighted distributions indicate the distribution of particle numbers amongst particle diameters. Such distributions provide essential information to understand the effectiveness of nucleation and seeded growth operations in crystallization or emulsion polymerization. With the data from a number-weighted distribution, we can plot a surface area-weighted PSD. This modification provides another way of characterizing our distribution. Here we designate the fraction of the total surface area within a given particle diameter bin with a small s, and the surface area weighted mean is labeled D32, often referred to as the solder mean. Such distributions indicate the distribution of surface area amongst particle diameters. This information is useful, for example, when our interest is in adsorption or surface reactions, such as separation processes or catalysis. Number-weighted distributions also provides for the generation of a volume-weighted distribution, which for a fixed density indicates a distribution of mass amongst particle diameters. The fraction here is the volume fraction, indicated with a small y. The volume-weighted mean is indicated D43, which is also known as the de Broca mean. Particle size often governs the performance and appearance of a colloid, and volume-weighted distributions indicate how much of a generated colloid is within a target diameter range. Ideally, measured particle size distributions could be collected and plotted with various weightings to provide a range of information. Unfortunately, this is generally not the case. Weightings for distributions are fixed by the experimental technique used to collect the data. For example, image analysis and microscopy produce number-weighted distributions. Light diffraction produces volume-weighted distributions, and dynamic light scattering produces intensity-weighted distributions. Furthermore, many techniques do not provide weighted diameter distributions, but actually measure surface areas or volumes. Although the software associated with the measurement equipment typically allows for the construction of different distributions from the primary or native data set, such transformations must be carried out with great caution, especially with multimodal size distributions. When used correctly, this transformation provides valuable information about the relative abundance of different particles. When applied indiscriminately, it can be very misleading. Here you are asked to repeat the previous example, but in this case the distribution should be volume-weighted. Rather than returning to the original particle count, the fraction of particles contained within each bin and the midpoint diameter for each bin is used to calculate volume fractions. We then plot the volume-weighted distribution over the top of the number-weighted distribution. It can be seen that this produces a significant shift to greater diameters as indicated by the higher mode. Also plotted is a cumulative fraction for the volume-weighted distribution from which the median is obtained. Also from the distribution data, the volume-weighted average is determined as well as the standard deviation. Often, the horizontal axis or abscissa of a particle size distribution is titled particle size or particle diameter. There are occasions where the particles are actually spherical and completely characterized by their diameters, especially when dealing with emulsions or some foams. However, for most sols, the particles are not spherical. In such cases, the size of the particle is often reported in terms of its equivalent spherical diameter, or its ESD. The ESD is the diameter of a hypothetical sphere that demonstrates the same behavior under the same test conditions as the actual particle. Shown here are just a few of the ways that ESD values can be defined. Now, the ESD value is directly tied to how the particle size is measured. For example, if the particle sizing technique measures particle volume, which is done in the case of a Coulter counter, which we'll discuss shortly, the reported equivalent spherical diameter of a given particle is reported as the diameter of a sphere possessing the same volume. If that same particle is sized using, say, capillary hydrodynamic fractionation, which we will also discuss, the reported ESD is the diameter of a hypothetical sphere that possesses the same elution volume as the particle. So again, it should be stressed an ESD value is not a property of the particle. It's a relative measure dependent on the technique used and the calibration standard utilized or the theory applied. Some of the more common techniques used for gauging particle size are listed along with the particle size range for which they provide accurate data. All of these techniques involved indirect measurements of dimensions gauged through other properties such as the scattering of light, rate of diffusion, sedimentation rates, ability to pass through a given mesh size, and so on. Even in the case of image analysis and microscopy approaches, the measurements are considered indirect because dimensions are estimated from two-dimensional representations of three-dimensional structures. There exists a great number of techniques for gauging particle size, which makes things, well, a bit overwhelming. But we can organize these techniques into a handful of categories. There are a few ways to do this. This slide shows one of the most common approaches, which is to divide techniques based on the degree the particles are separated for the measurement. Here, three categories are used, including ensemble methods, counting methods, and separation methods. Let's begin with ensemble methods. Methods in this category measure all particles simultaneously. Typically, a result for the entire sample is fit with a theoretical model to provide the particle size distribution. from which statistical characteristics are determined. The second category are the counting methods, which measure size-related properties of individual particles. These counts are then divided into a series of virtual bins based on size. This allows the particle size distribution to be plotted, from which the particle size statistics are determined. The final category for this scheme are the separation methods. In this case, the particles are physically divided and counted to provide data for constructing the particle size distribution, from which the particle statistics can be extracted. An entire course could be taught on approaches for gauging particle size. Here it's covered in just a few slides. So rather than trying to provide a summary of all the techniques currently being used in industry and academia, I will provide an example under each category. I've tried to select methods that you have likely heard of if you spent any time in an industrial or academic laboratory. Static light scattering, or laser diffraction, is an example of an ensemble method. The method involves passing monochromatic light from a laser through a dispersion of particles. Particles scatter the light, producing a pattern characterized by its intensity at various scattering angles. In quality modern equipment, greater sensitivity is achieved through the use of two light sources, including a log wavelength or red source, for example 650 nanometers, and a short wavelength or blue source, for example 405 nanometers. Also, numerous detectors are used, which are arranged in a semicircular fashion surrounding the sample to provide a wide range of detection angles. As light interacts with a particle, several processes can occur as shown, but the diffraction and the refraction are what produce data providing information on particle size. For larger particles, usually greater than about 20 microns, diffraction dominates, resulting in high-intensity signals at low angles. As particle size is decreased, refraction becomes increasingly more important, which produces patterns characterized by lower intensities at higher angles. The pattern is analyzed using either the Fraunhofer or Mie theories for larger and smaller particles, respectively, assuming spherical particles characterized just by their diameter. For this course, the emphasis is on colloidal systems. Thus, particles are generally small. Thus, plots of scattering intensity versus scattering angle is more accurately fit via Mie theory, which requires knowledge of the refractive indices of both the particles and the medium. Results provide volume-weighted distributions using volume-equivalent spherical diameters. Laser diffraction has many advantages, including fast, reliable, and non-destructive measurements of both wet and dry samples without the need for calibration. It's based on first principles. The reported particle size range is less than 5 nanometers up to 5 millimeters. However, this technique is known for having a very low resolving power. Furthermore, accurate results strongly depend on the quality of the optical property values entered, such as the indices of refraction and absorption, which are oftentimes just estimates. Also, the technique does not work when a system contains particles possessing different optical properties. An Electrozone or Coulter counter is an example of a counting method. It is a technique pioneered by Coulter for use in hospitals to count blood cells. It requires that particles be dispersed in an electrically conductive liquid such as water containing salt. The way it works is that particles are forced into an elongated glass tube through a finely bored aperture. Electrodes are located on either side of the tube. As the particle passes through, there is a spike in the electrical resistivity, which produces a peak in the measured voltage or current. The area of this peak is proportional to the particle volume. After several thousand particles have passed through the orifice, the data are converted into a particle size distribution. The resulting PSD is in terms of volume fraction versus ranges of particle diameters. The statistical values are volume weighted. The diameters are those of spheres having volumes equivalent to the particles, that is, the equivalent spherical diameters. The final distribution is corrected for coincidental counts. Advantages to this technique is that it works for particles ranging from about a half a micron up to several hundred microns. The equipment is calibrated with known standards and is easy to operate. The drawback is that the range of particle volumes is limited to about 30. Also, the accuracy of the equipment is better near the middle of the size range, and problems often occur when measuring particles near the lower limit of 1/2 micron. Particles smaller than this cannot be measured using this technique. Capillary hydrodynamic fractionation, or CHDF, is an example of a separation method. The way it works is that a dilute dispersion of particles is injected and passed through a fine capillary tube, which is only a few microns in diameter. As the liquid carries the particles, they randomly move about the tube due to Brownian motion, and at any instant, a given particle is moving with a velocity approximately equal to the liquid velocity acting at its center. The liquid flowing through the capillary tube has a parabolic velocity distribution. Thus, its velocity is minimized near the wall of the capillary tube and increases towards the center of the tube. If the particles are spherical, the closest their centers can approach the wall of the capillary tube is 1/2 their diameters. This means that particles with larger diameters on average are experiencing higher velocities than particles with smaller diameters and reach the end of the capillary tube faster. This separates the particles based on size. As they reach the end of the tube, their concentration can be determined using a detector, such as an RI, optical, or ultraviolet detector. This provides a number-weighted particle size distribution. Product information on CHDF claims that the technique works well for a diameter range of 0.01 to 3 microns. Advantages of this approach include fast results with little sample prep and ease of use. Also, measurements do not require extensive information on the optical properties of the particles or the aqueous carrier. The major drawback of this approach is its poor resolution. Also, it is restricted to aqueous dispersions and roughly spherical particles. It is important to emphasize that the results are relative to spherical calibration standards, and thus the equivalent spherical diameter is that of a sphere demonstrating the same elution time as the particle. Now, what we've covered over the last several slides are just 3 of a couple hundred different techniques that can be used to characterize particle size. Often, different samples require different approaches, and the use of multiple approaches can provide valuable information, which is not apparent from the use of a single approach alone. Being able to plan the best approach for characterizing particle size for a particular application definitely requires some training and experience. The formation of a hydrophobic colloid is a great way to combine materials which are immiscible in each other. As mentioned, the process of forming a solid requires work. The reversible portion of this work is retained in the system in the form of free energy from the new surface area generated. We are all familiar with the saying of what goes up must come down. This simply points out that lifting an object in a gravitational field increases its potential energy, giving rise to a force that will act to bring the object back down to the ground where it's more stable. For hydrophobic colloids, this could be rephrased as what is broken down must come back together. Again, the formation of a hydrophobic colloid from immiscible bulk phases increases the free energy of the system. The system responds by spontaneously returning to the separated bulk phases. The topic of colloidal stability is concerned with what forces dominate this process and how these forces can be manipulated. We begin this discussion by considering a single isolated particle in water. If this particle is dropped from the surface of the water, it experiences several forces. The most obvious is the gravitational force pulling the particle to the bottom. This is offset to a certain extent by the buoyancy force from the displaced water, but a solid particle with a density greater than the water will experience a net force pulling it down. As the particle settles, a third force comes into play, the drag force due to friction between the particle and the water. As the particle settles, these forces balance, and the particle reaches a constant velocity known as the terminal velocity. From the force balance, we come up with an expression for the magnitude of this velocity, which is directly related to the square of the particle diameter. Another influence on an isolated particle in water is Brownian motion. As you already know, this is caused by collisions between water molecules and our particle. This causes the particle to randomly translate in all 3 directions. On average, the kinetic energy of a particle, regardless of its size, is about 1 kT, where K is a Boltzmann constant and T is absolute temperature. From this, a velocity of the particle due to Brownian motion is found to be inversely related to the diameter of the particle raised to the 3/2 power. Now that we've identified the forces acting on an isolated particle in water, let's compare some numbers. If we assume a temperature of 20 degrees C and a solid particle with a density of 2,000 kilograms per meters cubed, which is typical of plastics, using the properties of waters, the velocities due to both settling and Brownian motion can be estimated. From these, it can be seen that velocities due to settling are higher for larger particles, while velocities due to Brownian motion are higher for small particles. The significance of this is easier to see if the ratio of the velocities are listed and the colloidal size range is marked, which shows that for colloidal particles, Brownian motion dominates. This dominance decreases with increasing diameter. Near the end of the colloidal domain is where settling starts to become a factor. What this shows is that particles tend to stay suspended in a dispersion for long periods of time within the colloidal size region. That is, particles have a certain degree of stability just based on their size alone. This completes our first lecture of Chapter 8.